Okay, so pop quiz time. What shape does a projectile make when it's launched through the air?
Hmm.
If you said a parabola, well, I mean technically right. It's
Right.
what we all learn in like physics class,
Yeah,
right?
that's that classic textbook image.
For sure. But get this, our deep dive today is going to blow your mind a little bit because it turns out those perfect parabolas,
Yeah.
they're actually a teeny tiny bit off.
Interesting.
We're talking a mind-blowingly small difference,
Yeah.
but a difference nonetheless.
Okay.
Our source for all of this is this fascinating article from Big Think that really digs into like the nitty-gritty of projectile motion. And trust me, there's more to it than meets the eye.
Right. Yeah. It all comes down to the assumptions, I guess, that we make to like simplify the physics, right? Like we
Yeah.
pretend the Earth is flat.
Okay, hold on a second.
Huh.
Flat Earth. I know we use models and stuff to make calculations easier, but come on.
It sounds crazier than it is, right? Think about it like if you're throwing a ball across a park, the curvature of the Earth doesn't really factor into your throw, right?
Yeah,
At least not in any way you'd notice.
that's true, yeah. I'm not exactly launching satellites over here when I toss a frisbee.
Right.
So this whole flat Earth thing, it's just a handy shortcut for like most everyday situations.
Exactly. Exactly. It's all about picking the right tool for the job. These simplified models work surprisingly well for most everyday scenarios because, frankly, the difference between, a true projectile path and a parabola over those short distances is microscopic. We're talking like 1 in a million kind of stuff.
So you're telling me my awesome Couve ball isn't technically a perfect parabola?
Huh.
My ego is slightly bruised. But okay, so we've got these simplified models that work well enough for, most of us, I guess. But then there's the real deal, like the hardcore physics. What's the actual shape a projectile makes if we factor in all the like complexities?
Believe it or not, it traces out a tiny, tiny section of an ellipse,
Really?
just like the moon orbiting the Earth.
Wait, seriously. So every time I chuck something, it's trying to go into orbit. It's just that.
The Earth gets in the way,
Uh-huh.
literally.
Right. If it weren't for the ground, who knows what kind of orbital chaos we'd be living in. But that makes me wonder though, if it really is this elliptical path, why don't we see it? Why does everything seem to like fall back to Earth in that familiar arc?
That's because every time a projectile hits the ground, it's like hitting the reset button
Oh, okay.
on the
Yeah.
trajectory.
Okay.
Same thing happens when a ball bounces.
Mm.
Each impact starts a new, almost perfect parabolic arc.
Okay.
And remember, over those short distances, the difference between that arc and a true elliptical path,
Yeah.
it's incredibly small.
So it's like a series of mini ellipses all like strung together but happening so quickly and over such small distances that our eyes just see like the classic parabolic curve.
Right.
That's actually really cool. But let's say just for fun that we could somehow remove like the Earth's surface from the equation. What would happen then? Would our projectile just keep on cruising in a perfect elliptical orbit?
Well, that's where things get even more interesting, and it all has to do with what's going on beneath our feet.
Okay, you've officially piqued my curiosity. What does the inside of the Earth have to do with all of this?
Remember how we talked about using a flat Earth model as
Yeah.
a simplification?
Yeah.
Well, there's another layer of simplification we often use, and that is assuming that the Earth's gravity is uniform everywhere.
Wait, hold on. You're saying that gravity isn't the same everywhere on Earth? I thought that was like a fundamental constant.
It's a common misconception.
Yeah.
Well, while the strength of gravity doesn't, change drastically from place to place, it's not perfectly uniform. Think about it. The Earth isn't a perfectly smooth, homogeneous sphere.
Right. It's like that whole jawbreaker analogy we talked about earlier,
Mhm.
right?
Yeah.
Different layers, different densities.
Exactly. We've got the crust, the mantle, the core, each with its own density and therefore its own gravitational pull. So even if we could magically get rid of the Earth's surface, a projectile wouldn't travel in a perfect ellipse.
So what you're saying is the inside of the Earth is kind of lumpy when it comes to gravity.
In a sense, yes. These variations are tiny, but they exist. And because of these lumps and bumps in the Earth's gravitational field, our projectile's path would be ever so slightly, well, let's just say it wouldn't be a perfect ellipse.
Okay.
More like a wobbly, slightly distorted one.
Okay, now my mind is truly blown. So not only do we have like the Earth's curvature to consider, but also the fact that like the inside of our planet is like a giant uneven gravitational mosh pit.
You could say that, and what's even more fascinating? These these tiny variations in gravity are incredibly useful to scientists.
Okay, now you have to tell me more because this is where I'm like starting to lose track of reality a little bit. How on earth can you use these microscopic variations in gravity to study something as massive and well as solid as the Earth's interior?
So imagine you're playing a cosmic game of billiards, but instead of a pool table, you have the Earth.
Okay.
Instead of billiard balls, you have things like seismic waves from earthquakes.
Okay, I'm following so far. Giant Earth billiard table, invisible earthquake billiard balls.
By studying how those waves travel through the Earth, how they speed up, slow down, or even change direction, scientists can create a map of the Earth's interior. They're essentially using those waves to see inside the Earth. Kind of like how, doctors use X-rays to see inside the human body.
That's amazing. It's like we can use these tiny variations in gravity to unlock the secrets hidden like deep beneath our feet. But okay, let's be real for a second. As fascinating as all of this is, how often do we actually need to like worry about these tiny wobbly ellipses? I mean, it's not like I'm factoring in the density of the Earth's mantle when I like play catch with my dog in the park.
You're absolutely right. For most everyday experiences, those simplified models we talked about earlier work perfectly fine.
Hmm.
But there are situations where understanding these subtle effects becomes, crucial, especially when we're dealing with very precise measurements or very long distances.
Okay, okay. I can see that. You wouldn't want to be off by even a millimeter when you're building a skyscraper or something.
Yeah.
Exactly. And it's not just about, physical structures either.
Yeah.
Think about things like satellites or long-range missiles. Those objects are in motion for extended periods.
Hmm.
And even the tiniest variations in gravity can add up over time, affecting their trajectory.
So it's like the longer something is in motion, the more those tiny gravitational lumps and bumps
Yeah.
start to matter. It all comes back to like choosing the right level of precision for the job, right?
Precisely. It's about knowing when a simplified model is good enough and when you need to, bring in the big guns, so to speak. It's
Yeah.
it's a key concept in physics, but honestly, it applies to so many areas of life, wouldn't you say?
Totally. It's like choosing the right tool for the job, right?
Yeah.
Sometimes you can get away with a simple estimate and sometimes you need to, break out the calculator and go full on engineer. But all this talk about gravity got me thinking. We've talked about Earth's curvature, its lumpy interior, but there's one more factor that seems like it should play a role here, right? Like the Earth's rotation.
Right.
Does spinning at hundreds of miles per hour while all of this is happening, does that affect things too?
You're on a roll today. You're absolutely right. The Earth's rotation does have a subtle but fascinating effect on projectile motion. Imagine for a moment you have two cannons.
Two cannons. Okay, I'm intrigued. Where are we putting these cannons?
Let's place one on the equator, aiming at east, and the other one also on the equator but aiming west.
Okay.
Now, when both cannons fire a projectile simultaneously, something interesting happens.
Okay, I'm picturing these cannons on the equator pointed in opposite direction.
Mhm.
Let me guess. The projectiles don't land in the same spot, do they? Even if we factor out things like wind resistance.
You got it. The projectile fired eastward in the direction of the Earth's rotation actually gets a slight boost in velocity. It's like the Earth is giving it a little push.
Yeah.
Meanwhile, the projectile fired westward against the Earth's rotation experiences a slight decrease in velocity.
It's like trying to run up a down escalator versus running down one.
Exactly. It's a relatively small difference, and it's often masked by other factors like air resistance, but it's there. The Earth's rotation is just one more variable in this grand equation of projectile motion.
So let me see if I've got this straight. We've got Earth's curvature turning our parabolas into like mini ellipses. The lumpy interior kind of messing with gravity and making those ellipses all like wobbly, and on top of all that, the whole planet is spinning like a top, giving some projectiles a boost and others a bit of a drag.
You got it. It's amazing that something as seemingly simple as throwing a ball is actually this intricate dance of forces, all acting on each other in ways we often don't even realize.
It really makes you like appreciate the mind-boggling complexity of the universe, even in the most like everyday things. And it
Right.
goes to show you those simplified models we learn in in school. They're great starting points, but there's always more to the story, isn't there?
Absolutely. There are hidden depths to explore in even the most familiar concepts. And that's what makes learning about science so endlessly fascinating.
Well said. So to quickly recap our deep dive today, we learned that those classic projectile parabolas we all know and love are actually just tiny segments of ellipses masked by the fact that, well, the Earth gets in the way. We also dove into how the Earth's curvature, its lumpy, uneven interior, and even its rotation all influence a projectile's path. Who knew there was so much going on beneath the surface of such a simple concept?
It's a great reminder that even in the things we think we understand, there's always more to discover, more layers to peel back and more to learn.
Couldn't agree more. So the next time you see a ball flying through the air, take up a moment to appreciate the intricate dance of forces at play. It's a little slice of cosmic ballet happening right before your eyes. And hey, if you want to really impress your friends, you can tell them all about those wobbly ellipses and that sneaky Earth spin.
I'm sure they'll be very impressed.
That's all the time we have for today's deep dive. Thanks for joining us on this journey into the surprisingly complex world of projectile motion. Until next time, keep those minds curious.